Welcome to the Spatial Temporal Earth Pattern model. This model shows the relationship of meteor impacts, especially the largest meteor impacts, cratons, and world-class mineral deposits. Davis and Hirsch, 1981, view modeling as an art that requires adopting a proper strategy, and this necessitates acknowledging the logic and assumptions on which the model is based. The basic assumptions and logic behind the spatial temporal earth pattern model are as follows. The first basic assumption is that the Earth was impacted by much larger and many more meteors in the late heavy bombardment, that is 4.2 to 3.8 billion years ago, than any subsequent period in Earth history. The circumference of major meteor impacts are deep faults, known as listric faults. These deep faults allow access to abundant heat for long periods of time. World-class mineral deposits occur where the greatest amount of internal thermal energy, that is heat, was present for the greatest length of time. World-class mineral deposits are on the margins of thick lithosphere cratons. All five of these assumptions can be supported by facts presented in the geological literature. And number 6, the logical conclusion from all of these facts, these assumptions, is that thick lithosphere cratons originated from the largest meteor impacts. This fairly recent quote by Bodke, 2017, on the late heavy bombardment is, quote, "Heavily cratered surfaces on the Moon, Mars, and Mercury show that the terrestrial planets were battered by an intense bombardment during their first billion years or more." And of course, included in the terrestrial planets is the Earth. This information has led directly to the discovery of the spatial temporal earth pattern and its relationship to world-class deposits. This model of early Earth bombardment is the basis of the spatial temporal earth pattern. The Moon is being used as an analog, always keeping in mind that the gravitational attraction of the Earth is 6 times greater than that of the Moon. And of course, this difference in gravitational attraction will mean that the Earth will have been bombarded by many more meteors and also by much larger meteors. It is proposed that each of the major meteor impacts would leave a permanent scar in the mantle, lesser meteors would disappear through erosion and other processes here on Earth. These permanent scars in the mantle become templates. They become accidental templates, which will be discussed later on in more detail in this presentation. One can see from this model that the largest meteors impacted the Earth in the first few 100 million years. Towards the end of the first billion years, meteors had diminished in size and in number. The Earth's continents originated from the largest meteor impacts. From a recent publication by Johnson et al. 2022, quote, "During the billion years following accretion, Earth witnessed a barrage of bolide impacts that caused large-scale melting and recycling of the crust. Whether or not this bombardment ended with a cataclysmic, that is, the late heavy bombardment, crater densities on the Moon, and other inner solar system bodies shows that the impact rate declined sharply between 3.9 and 3.5 billion years ago. With a surface area more than 10 times that of the Moon, and a gravity well more than 20 times as deep, Earth would have endured an impact flux 20 to 300 times that of its satellite. As one will discover below under the heading Craton, it was as recent as 2015 that the very first paper was published relating large meteor impacts and Cratons. As one proceeds through the rest of this presentation, it will become obvious that the mention of meteor impacts and the relationship of those impacts to Cratons, mineral deposits, world-class mineral deposits, is becoming more prevalent. However, when an idea's time has come, there is convergence. One of the better examples of convergence is the discovery of natural selection by Charles Darwin and Alfred Russel Wallace, essentially at the same time back in the 1800s. This is the saturated impacting of our satellite, always keeping in mind that the Earth would have endured an impact flux 20 to 300 times that of our Moon. The circumference of major meteor impacts are deep faults. The viewer is reminded that the Moon, in respect to the model presented here, is being used as an analog. So, for example, the deep listric faults observed for major meteor impacts on the Moon will occur here on Earth as well. However, the dip angles may differ. An artist's rendition of a major meteor impact with a listric faults going to considerable depth well into the mantle. The current approach to attempt to understand deep continental roots and Cratons themselves is by implementing plumes. And of course, the plume-derived melt residue is based on the assumption that all patterns, all processes within or on the Earth are terrestrial in origin. And of course, that assumption is not valid. the Earth is part of a much larger, much grander system, even the system of our own solar system. Perhaps the plume-derived melt residues can be replaced by meteor impact-derived melt residues. The Earth-centric view prevents any real and factual evidence for the evolution of our Earth. Cratons. Hudson, in her 2015 paper, appears to be the first person to suggest that there is an impact origin of Archean cratons here on Earth. The following is an important quote from Pearson et al. 2021 on deep continental roots and cratons. Quote, "The formation and preservation of cratons, that is, the oldest parts of the continents, comprising over 60% of the continental landmass, remains an enduring problem. Key to craton development is how and when the thick, strong mantle roots that underlies these regions forms and evolved." The longest-lived cratons were assembled during Mesoarchean and Paleoproterozoic times, creating the stable mantle roots 150 to 250 kilometers thick that are critical to preserving Earth's early continents and central to defining the cratons. And ultimately, from Pearson's 2021 paper, the following quote, "Cratons produce over 90% of the world's gold and platinum and almost 100% of its diamonds. The properties of cratonic lithospheric roots are becoming increasingly recognized as key factors in the topographical expression of continents, lithospheric volatile storage, and the location of many metal deposits." This quote, more than any other, explains the importance of cratons in respect to understanding their origin through meteor impacts and their relationship to mineral deposits. There are several important takeaways in respect to this cross-section presented by Pierce et al. 2021 in respect to deep continental roots and cratons. The first is the actual extent of cratonized lithosphere, as indicated by the red line, is at different depths. Second, note that the ages of the cratons are correlated directly with the depth of the craton roots. The older the craton, the deeper the root. The importance of these two observations will be developed in the next few slides. The meteor impact crater on the Moon, known as Oriental, hit the Moon 3.8 billion years ago, creating one of the Moon's largest craters. The Oriental meteor crater can be seen in the lower right-hand side of this slide. The simulation for this meteor impact, that is the Oriental, created by a 64-kilometer diameter meteor, is shown in the box to the left. The simulation shows half of the crater created. Note the deep keel, or root, shown as dark red on the left-hand side of this simulation for this meteor impact. The largest meteor impacts and depth of penetration. The Oriental impact simulation reveals that the root is greater than 200 kilometers, which puts it well into the Moon's mantle. This figure is very much in line with the roots of Cratons here on Earth. It would be reasonable to expect larger meteors with greater mass to penetrate to greater depths. This is supported by combining the video presented above by Marchi 2014 and the cross-section presented above by Pearson. The conclusion is that Hadean meteor impacts 4,600 to 4,000 million years ago were the largest to ever hit the Earth and penetrated the deepest, creating deeply rooted circular structures that manifest as cratons. The following quote by Perchuk et al. 2020 titled Building Cratonic Keels in Precambrian Plate Tectonics is the best possible support for the current model presented here. As one goes through this presentation, you will see that each of the points brought up by Perchuk in the previous quote are in total agreement with the conclusions presented here. They are 1. The ancient cores of continents, that is, cratons, are underlain by mantle keels. 2. The mantle keel, that is, the roots of these cratons, consist of melt-depleted mantle peridotites. Other processes that go on within the mantle keels causes superficial features such as pseudo-tacholites and shatter cones to completely alter and disappear. 3. The roots are mechanically resistant. They're buoyant and up to 350 kilometers thick. 4. The roots have remained isolated from the hotter and denser convecting mantle for more than 2 billion years. 5. Mantle keels formed only in the early Earth, that is, approximately 1.5 to 3.5 billion years ago in the Precambrian eon, and they have no modern analogues. And I would add, number 6, the mantle roots were created by large meteor impacts. The largest meteor impacts and faults. Zuber et al. 2016 make the following comment in respect to the Oriental faults. Quote, although these faults may be listric and the dip angle may decrease with depth, the 50-degree dip angle indicated by hydrocode simulations is consistent with prominent changes in crust mantle boundary depth. The next few slides show the listric faults in the hydrocode simulation. The listric faults as revealed from the hydrocode simulation. These listric faults are the same faults mentioned by Grieve and Macetas in 1994 paper showing the economic potential of terrestrial impact craters. These are the accidental templates left by fossil impact sites and are obvious because the meteor crater is still present. Meteors, cratons, and ore deposits. This paper by Groves and Santosh, 2021, is another example of convergence. Quote, although most economic geology research is concentrated at the deposit or mineral system scale for a single well-defined deposit group with a consistent metal association, there are both academic and economic advantages in considering the similar geodynamic setting of deposits having contrasting metal compositions that are traditionally considered unrelated. As an example, there are a range of mineral deposit types or systems that are spatially associated with the margins of long-lived, relatively cold, buoyant Precambrian Cratons, or lithosphere with thick mantle lithospheric roots. World-class mineral deposits occur where the greatest amount of internal thermal energy, that is heat, was present for the greatest length of time. The conclusions of Billingsley and Locke, 1976, have proven to be especially insightful. In their structural analysis of the ore districts in the United States in a continental context, they concluded that giant deposits occur where there are superimposed deformations of different ages, which strengthen the rocks, making them competent to carry channels to depth. These deep penetrating breaks permit the passage of heat and associated products such as magmas, metamorphism, alteration, and mineralization from depth to the surface. The reactivation of pre-existing structures is a major theme for many hydrothermal mineral deposits. World-class deposits on the edge of circular features can be seen in eastern Australia, especially using magnetic data. Since our interest is patterns, we need not be concerned with absolute magnetic values. It will become obvious the advantages of using grayscale images and binary slices in analyzing our magnetic data. The grayscale magnetic image for Eastern Australia. There is considerable information in this published magnetic image. There are repeating patterns. Please note that Mount Isa, a world-class deposit, is an exception in this case because it occurs on an arc instead of the edge of a circle. This exception by Mount Isa can be explained by using macro-scale patterns by observing macro-scale patterns in Eastern Australia using binary slices of gravity data. The grayscale gravity image of Eastern Australia. The advantages of using grayscale images will become obvious as one proceeds through this presentation. Grayscale images have 256 gradations of gray, 0 being black and 255 being white. So in the following images, any pixel with a value greater than the designated number is white, and any pixel less than that number is black. it becomes obvious that after a certain point, information is actually lost. The image with maximum information. The interpretation. The compressional force of Australia's movement northward causes mantle and crustal material to flow eastward. One can see here the advantage of using the gravity binary slice map for interpretation compared to the filtered gravity map, which is much more complex. The proposed flow in an easterly direction of mantle material in Central Australia is identical to the eastward flow of mantle and crustal material in Southeast Asia. This is shown in the next slide. The blue arrows indicate the northern migration of India, and the red arrows indicate the direction of flow of mantle and crustal material. It is proposed that this eastward flow of mantle and crustal material has dissected the annulus on which the Mount Isa deposit occurs. Originally, the Mount Isa deposit was on the outer edge of a circular feature that has been distorted and dissected. Seismic tomographic analysis of Australia supports this interpretation. Seismic tomography allows the mapping of velocity perturbations in the Earth's mantle that indicate mantle temperature variation. Waves tend to travel faster in colder regions than in hotter ones. This is due to density contrasts related to temperature. Colder materials are more dense than hotter materials, allowing them to transmit waves at a higher speed. In the following movie, the thick blue bars are the fast axes of seismic anisotropy. The slow axes would be orthogonal to the fast. They are represented by thick black bars. The thin black bars are the axes showing minimum flexural rigidity of the lithosphere, that is, mechanical anisotropy determined using topographic and gravity data sets. The thin black bars are generally orthogonal to the blue bars and indicate the direction of mantle flow. Here we can see that the thick black bars coincide for the most part with the thin black bars. This shows that the data sets for seismic, topography, and gravity for all of Australia agree in respect to mantle flow. This was the proposed movement of the mantle material flowing in an easterly direction from our magnetic data. However, considering the data from gravity and topography, there is a northeasterly component in this eastern flow. It is this northeasterly flow of mantle material that has modified the Mount Isa, the proposed Mount Isa Meteor Impact. It is quite possible that the circle here for the proposed Mount Isa Impact is much smaller than the original impact itself, with both compression and extension taking place subsequent to the impact. Proposed meteor impacts from around the world. Part of the problem regarding recognition of the remnants of impact events is the fact that terrestrial processes, such as sedimentation, erosion, plate tectonics, either cover or erase the surface expression of the impact structures here on Earth. One of the better examples of a proven meteor impact is the 66 million year ago Chicxulub impact in the Yucatan Peninsula of Mexico. Chicxulub is a complex meteor impact, which means that it has both an inner and an outer ring. One of the characteristics of complex meteor impacts is that they have relatively invariant morphological and structural properties as a function of diameter. Hence, the ratio of the inner circle to the outer circle stays constant for meteor impacts here on Earth. So the Chicxulub impact can be used as a template. As an aside, it is important to know that this ratio of inner circle to outer circle varies from planet to planet. One might recall that the Oriental meteor impact on the Moon has a very different ratio than does the Chicxulub deposit here on Earth. The Red Sea Meteor Impact. In the next few slides, we will be using the Chicxulub templates to recognize the Red Sea proposed meteor impact. Please recall that the Chicxulub structure is 200 kilometers in diameter, where the proposed meteor impact at the Red Sea is 4,000 kilometers in diameter. There are meteor impacts on the Moon that approach this size. Several features are revealed when the Chicxulub template is used on the proposed Red Sea Meteor Impact. The first is the radial center in eastern Turkey, located on the outer edge on the circumference of the proposed Red Sea Meteor Impact. To understand why this is important, please have a look at our presentation, Oil and Gas Fields, Arabia, Europe, Russia, Africa, Why and Where, on our YouTube channel. Second, notice the location of the Strait of Hormuz, which is indeed a very strange topographic feature. Like the radial center in eastern Turkey, the Strait of Hormuz is located on the outer edge, the circumference, of the proposed meteor impact. And number 3, note that both ends of the Red Sea are constricted, closed, and those constrictions, coincide closely with the outer edge, the circumference of the inner circle of the proposed meteor impact. The geology to the east and to the west of the Red Sea helps support the model that we are presenting here. The geological map presented by Rasool in 2019 shows the Arabian Shield to be northeast of the Red Sea and the Nubian Shield southwest of the Red Sea. The significance of these shields and platforms are presented in the next slide. Shields, platforms, and cratons. Quote, the extensive central cratons of continents may consist of both shields and platforms. A shield is that part of a craton in which usually Precambrian basement rocks crop out extensively at the surface. By contrast, in a platform, the basement is overlain by horizontal or subhorizontal sediments. It becomes obvious that our proposed meteor impact of the Red Sea coincides with the craton consisting of shields and platforms. Another proposed meteor impact in the Basin and Range, USA. Here we are using a different data set to prove the presence of a meteor impact. As Grieve and Pilkington 1996 point out, another important feature of a proposed meteor impact site is the presence of a negative gravity anomaly. A gravity map for the western USA. The location of shatter cones and pseudo-tachyte-bearing rocks indicating the presence of a meteor impact. The proposed Beaverhead meteor impact in southern Idaho, USA. Please see our presentation titled World-Class Gold Deposits in the Basin and Range, USA to understand the significance of this proposed meteor impact on gold deposits in the Basin and Range. The photo to the right is shatter cones from the Beaverhead meteor impact structure, while the photo to the left is pseudo-tachytes from the Redford meteor impact structure in South Africa. The copper deposits of southwestern USA, another way of detecting meteor impact sites. The data set used to reveal the presence of meteor impact will be magnetics. One of the datasets available and one of the techniques available for detecting meteor impacts is looking at short wavelength variations in tone in magnetic data. A reduced to pole magnetic map for the southwestern USA. Here we'll be looking at change in texture to detect subsurface structures. That subsurface structure is circular. This circular structure is proposed to be a major meteor impact. That is 900 kilometers in diameter. An impact within an impact and the relationship of those impacts with world-class copper deposits in southwestern USA. Here we can see the impact within an impact and the relationship of those impacts to world-class copper deposits. Impacts within impacts are common on the Moon, so it is reasonable to assume that the same thing has happened here on Earth. The evidence for the smaller impact, 450 kilometers in diameter, can be seen on our world-class copper deposit Southwestern USA on our YouTube channel. A recap of our model. As mentioned previously, when an idea's time has come, there is convergence. A perfect example is this recent publication, 2021, by Groves and Santosh, titled Craton and Thick Lithosphere Margins, the Sites of Giant Mineral Deposits and Mineral Provinces. The relationship of cratons and giant mineral deposits was introduced many years prior. One can read this introduction in the reference listed below. Groves and Santosh go on to state that nearly every type of mineral deposit is found on the edge of a craton. And as well, Groves and Santosh acknowledge the importance of the deep extensional fault systems that developed on the craton margins. This map shows the 55 cratons here on our Earth with roots to a depth of at least 150 kilometers. Geologists who have specialized in meteors and meteor impacts warn that circular features here on Earth are not diagnostic in determining the site of a meteor impact. However, when additional data indicating the presence of a meteor impact is presented, I think one has to pay attention to circular features. That additional data is the concentric zoning of cratons in Canada around Hudson Bay. This is shown in the next few slides and leaves little doubt that Hudson Bay was not only an extremely ancient meteor impact, but a very large one. It becomes obvious from this bullseye target that Hudson Bay is a perfect circular structure coinciding with our proposed meteor impact. As well, please note that the various cratons, including Slave and Ray and Superior, form a near perfect circle centered on Hudson Bay. It was mentioned previously that the terms accidental templates would be discussed in more detail. Ordoliva, in his 1994 book titled Geochemical Self Organization discusses the possibility of many types of internally generated templates existing in self-organized geochemical systems. Mineral deposits are a perfect example. He also mentions templates that are accidental, those that have been imposed on a system through some external agent. Meteor impact structures are a perfect example of this type of accidental templating. An accidental template in southeastern Australia. The Deniliquin-Booligal proposed meteor impact. This total magnetic intensity map comes from a recent publication by Glixon 2022 titled The Geophysics and Origin of the Deniliquin Multi-Ring Feature in Southeastern Australia. The multiple rings of this feature are quite obvious. A field inspection along the circumference of the proposed Deniliquin-Booligal Meteor Impact discovered sheeted quartz veins with abundant arsenopyrite at a location known as Coleman's Hill. We eventually renamed this the IDYLWAY Prospect. Our exploration results for the IDYLWAY Prospect can be seen in our presentation, the IDYLWAY Copper-Gold Prospect, New South Wales, Australia, on our YouTube channel. As an aside, we have used the Chicxulub template to delineate the Deniliquin-Booligal impact. Conclusions and contributions. Large, ancient meteor impact sites can be detected using various data sets. That is, for example, magnetic, gravity, topographic, and others, incorporating various techniques of data analysis. Large, ancient meteor impacts created Cratons. The margins of Cratons and meteor impacts are deep faults. These deep penetrating faults permit the passage of heat and associated products such as magmas, metamorphism, alteration, and mineralization from depth to the surface. Our datasets now allow us to predict the locations of the resulting patterns, which are accidental templates. And finally, these world-class mineral deposits occur at the margins of these predictable patterns.